That was good. All right, you introduce me. That's going on. Yeah, you need to put up for a second. So also tell me to get my water. We're on time. Yeah.
Hello. If you folks in the back can come take your seat, please. Come take your seat.
There's real serious.
Stuff
happening up here.
Or fuck off. I guess that's fine too. It's like taking your seat. You're good. All right, real quick before this talk starts, you have until the end of this talk to submit your entry for Soldering Olympics Round 1. So if one of you is soldering in the room while watching this, that's awesome, actually. But you can still get the Round 1 boards later today, tomorrow, etc. But we'll be moving on to Round 2 after this talk. Some additional announcements. There is a pinball tournament going on in the chill out room with the Attack from Mars pinball machine. So go get a high score, vanquish your enemies, etc. Additionally, all the contests should be running. If there's any questions, let me know. Later tonight in the Hardware Hacking Village is the demo party. At the same time, in the Capture the Flag room is the amateur radio license testing. So if you're signed up for those, then do those at that time. Otherwise, later tonight, 7:30 in this room is our big banquet dinner. So come enjoy dinner, have fun, play games. It's board game night, etc. If you have any questions, ask at registration or hit me up. Ideally, registration. But other than that, coming up next is Hacking Doodleburg, reverse engineering children's toy firmware by our very own John King.
Nice. Bye.
All right, welcome. This talk has assembly in it on the screen. So if you want to read assembly and fully participate, I recommend you move kind of forward in that way. If you want to sit quietly in the back and not understand half of it, that's okay too. All right, yeah, I'm JK. I do stuff. I'm here talking on behalf of myself, not my employer. My employer does not care one bit about Mr. Pencil. So before we talk about what Mr. Pencil is, we talk about where we got Mr. Pencil. So me, Cezio, Standard Error all went to Target 2 years ago at LayerOne. It's a few blocks that way. And we browsed the toy aisle just looking for things to hack on. And you see this. That's got a keypad, like a little keyboard. So, of course, you buy that to go hack on it, right? Maybe it runs Linux. Who knows? Especially $29.99. It's very affordable. So this is what it looks like. Rather than tell you what it is, let's see if we can show you. Of course, there's no audio. Why would there be no audio? It's fine. Yeah, this is Mr. Pencil starting up. He dances, he sings, and you can draw on him and whatnot. And yeah, so now we know kind of what Mr. Pencil is. Who is he? It's a much more important question. He's best friends with Mrs. Paintbrush, and he likes to draw. This is the sum total of all Mr. Pencil lore on the internet. He's got a list of credits, though. Like, he's been in some stuff. He's got some toys. By the way, all 3 of those toys are in the Hardware Hacking Village. So if you want to go, like, explore some new hardware hacking Mr. Pencil territory, it's all there for you. Please take them apart. Please reverse engineer them. Please get arbitrary code execution on them. The games, who knows? But the toys are here for you to play with. All right, so now you've bought this thing, what are we actually trying to do? So, like, you take it apart, cool, there's electronics in there. Like, what is your objective? The initial goal was to make it speak profanity. As a children's toy, this is just a natural goal. It's kind of self-evident. But we want to work on our skills and sort of learn how to do this stuff against a target that isn't made to be reverse engineered. There's nothing about this is meant to be friendly. They're meant to be mass manufactured and sold for $29.99 in Target. And then the kind of our stretch goal is we want to get arbitrary code execution on it if it's possible. So you open the thing up, and this is what you see. There's plastic, there's wires, there's a circuit board. So you kind of look at it for a minute and kind of see what you see, and I'll show you what I saw. So there's a touch display on the back. You can't see it. There's a speaker, keypad, there's some LEDs, takes some batteries as a power switch, and a circuit board. Cool. But you look a little bit closer, what do you see here? Like kind of your initial sort of triage of taking out this piece of hardware. Well, I see a big blob. We have no idea what's underneath it. We see a smaller blob and some wires coming out of it. There's also a crystal that says 8.000. I don't know what that means, but maybe it's it's 8 gigahertz. That's probably what it means, right? So we flip over the board, look at the back. Do we see anything interesting here? Well, one interesting thing that we see up there at the top, there's an 8-pin chip. After a while, you'll recognize that profile. That's a SOIC8 is the name of that form factor, and these are commonly used as flash chips. So you zoom in, you go look up that part number on Google or ChatGPT or whatever, and you don't find it. That part number does not exist on the internet, but there's a very similar one that it looks like they copycatted or ripped off, made by Winbond. So you pull that data sheet and you kind of learn what wires do what, and you want to get the data off. So flash chips, they're like little hard drives sort of in chip form. It's the exact same technology as SSD. It's flash memory. So you can write to it, you can read from it. So this is being used as something sort of like a hard drive by Mr. Pencil. So what you're supposed to do is go get a nice kit, hook up this beautiful clip to the chip, and then use your very professional software to dump the flash chip. That's not what happened. Because remember, we're at LayerOne during all of this. So we have to work what we have. We borrowed a dev board from somebody, tore apart an Ethernet cable, soldered directly to the chip, and then wrote a flash dumper like in C, and managed to get the flash out. So you go, once you dump the flash out, all this data, there's about 4 megs of it. And you just look at the hex and just see what's there, right? You run strings on it. You do kind of basic triage on the data. And this is what you see. It's a bunch of hex that probably doesn't show up very well on that screen. But in there's a little bit of text. There's English text. It says name 1, name 2, name 3. And you're like, well, that means my dump worked. I didn't get random bytes back. But what does that mean? What is name 1, name 2, name 3? Well, if you play with Mr. Pencil a little bit, you'll kind of go into one of these menus where the kid can put their name in and then practice like drawing it, right? So this is actually one of the few parts of Mr. Pencil that gets written to Flash as well as read. So you do what you do. You modify your Python script to try to write to the Flash instead of reading from it. Can you change these texts, these name 1, name 2, name 3? And it turns out you can. You can make it say layer 1 2024, and you're done. That looks like arbitrary code execution, right? We're finished? No. All you've done is changed a little bit of text on a particular screen that you have to navigate to. But it does prove that the chip is writable, and you have some sense of that it's actually using it to do things. It's not extra. Okay, so you skim through further in the memory dump. Is there anything besides name 1, name 2, and then gibberish? And you find this. That probably also doesn't show up very well, but you can see by all of the censorship that there's some nasty words down there. There are over 1,000 pieces of profanity, slurs, just bad words for some values of bad, just in this giant list. And I'm not sure why they're there yet, but we're going to figure it out here shortly. So you stare at this. Once you kind of get over the shock value of how offensive these words are, my favorite is humpiest. Most humpy, I guess. But everything you can think of is in there. So you look at like, what's the structure, right? Can we learn anything from this besides just there's funny words? So you see some patterns, right? So all the H words are together. The words run together. There's no delimiter. There's no like null byte or a space, right? There's no FF separating the words. They just kind of like smash together. But you notice a few other things that are more subtle. The longer words kind of go together and the shorter words go together. So they're clustered by length for some reason. And there's a little bit of binary like gobbledygook at the beginning of this string of H words. So you kind of use that as your starting point and figure out what does this all mean? So eventually what you can find is that binary gibberish that came before all the words, those are pointers into portions of that blob of words. So you have a pointer for the words that are 0 letters long. There aren't any, go figure. 1 letters, there aren't any. 2 letters, there aren't any. Then you get to 3 letters, there aren't any. But then when you get to 4 letters, that points to the beginning of the 4-letter words. I've replaced the 4-letter words here with nice ones like halo, hero, home, hope, so that I can like show you the structure better. They're much more offensive than the real Mr. Pencil. If you want to go see the original list, go dump Mr. Pencil when we get out of this talk. and you can go see all the bad words. But yeah, up to 12 letters long is how far the pointers go. So cool. This is for a single letter. They've obviously grouped them by word length, and each kind of grouping ends in an FF. So let's zoom out a little bit more. So for each letter, how do we organize those? Well, if you scroll up in the hex dump, you'll find more pointers at the top that point to kind of each letter. So in this way, you can now find any word of any length with any letter if you follow the pointers, which is what their code does. So cool, we reverse engineered this dirty word list. What's this for? Can we do anything interesting here besides just play with dirty words? So it turns out when they type their name in, like name 1, name 2, name 3, because they want to spell it, this is to prevent them from like putting bad stuff in there. So I formulated a new dirty word list from scratch that has the 1,000 most popular names in the US in it. So the kid can't put their name in. All they can do is write curse words in it. So you can't say Harold, but you can say humpiest as your name. There's actually another set of words. There's 7 of them at the beginning, and they're like the really bad words. Like they have an additional check. I have not defeated that yet, so that's kind of a stretch goal for you guys. Go defeat the check that lets you like not put the F word in your name. So what else can we look at? Well, what else is in here besides this dirty words? So here's some gibberish, but if you stare at it long enough, you'll notice some patterns. And if you visualize it as binary instead of hex, these patterns are a little bit easier to see. So I've highlighted all the zeros and kind of left the ones blacked out. And it may look random at first, but you'll notice there's a lot more zeros than ones. And the ones tend to come in clusters or lines. They're not just like sprinkled randomly. So what this can indicate is graphical data, right? Because whenever you draw lines, they kind of like colors sort of cluster together. They're not just like noise. So what you can do is visualize this with Python. You can, instead of looking at an XXD where it's like ones and zeros, you treat every zero like a black and ones as a white, or vice versa. And then you kind of vary the width, like how wide is a row when you visualize it. And you can kind of do this. So if you pretend that this data is 22 pixels wide, you get what's on the left. But if you pretend it's 31 wide, you get what's on the right. And you can see there's obviously structure there. It's not random data. So that's stride 31. If you go to stride 32, it looks like this on the right, where you have the kind of black and white image. Do I have a laser pointer? Let's see. Laser pointer. I do. So yeah, if you kind of treat each row like it's 32 pixels wide, then you get this graphic, and then there's also a double of every single one of them. So this is sort of like, it looks like the inverse almost, but if you play with it long enough and you treat the top one as if like the ones are light gray and the bottom image, like the copy, is dark gray, and then you overlay them, you get this very pretty like shaded image. So what else is in this like this sprite data? We found the pixels. We kind of played with it manually to find what the width of the graphics are. But when you look at Mr. Pencil, they're not all 32 pixels wide. They vary. So you can't just pretend to be 32 and just dump the whole memory. It doesn't work. So we look above that. We look right before those pixels. Kind of like the header that was before the dirty words. We look at the gibberish before the pixels. And we see this sprite header. So take a moment, kind of look at it and see if you see anything that's kind of structural. And then I'll show you what merged out of it. So the width is kind of weird. They do something interesting here so that things line up on byte boundaries, so it's faster to draw. But they have the height and they have the width. And then there's this magic number that you can use to find all the sprites. So if you do that, if you look at this magic number and then you write some code to interpret that header, and then you visualize all the sprites, and then you set it to music, you can make a music video out of all of the... let's see if it goes. It's not wanting to go. That's okay. Why is the video not going? Okay. No worries. There's a bunch of sprites. I pulled out the interesting ones. It's a bunch of cute graphics of Mr. Pencil. But the ones that are more kind of weird are these ones. You have what's obviously some kind of like debugger diagnostic menu. It shows a battery, and then these failed and okay, the calibrate stuff. There's a little tiny like font here that might be useful to use later. But the rest of it is just kind of like graphics of pencils dancing around. Again, go play with it in the village and you'll see all of them. So what else can we do besides just look at this kind of raw flash dump off this external chip? So the other thing that you can do, instead of just reading off the chip directly, is you can hook up a logic analyzer and you can watch the wires between the microcontroller onto the big blob and the SPI flash chip that we just dumped. So you're not going to see any new data probably because you already dumped it all, but you'll get to see the timings and when it reads what, and what shows up on the screen when it reads it, or what plays out of the speakers. So you can use that to correlate where things are in the flash chip that you haven't identified yet. So this is an example. We see them when it first boots up, it reads from like the address 20, and it kind of goes like 1 byte at a time, and then it reads 8 bytes further. And what it's doing is it's XORing them together as a checksum. So this thing like checksums its own flash, which is kind of wild, but yet we can change our name and it doesn't care. So there's some really kind of odd behavior here. Or kind of going with the graphical theme, if you watch the reads, whenever it shows an animation, you can see it reading from those spots in the flash that we found those frames of animation. And you can kind of confirm, oh, okay, that's how it does that, and that is what it's displaying. And then you'll also see other reads that are interspersed with it. Those are probably the audio, is the idea. So we also, there's code in here too. So you can see when it's running what code. So there's kind of like this dynamic reverse engineering thing that's going on here. It's not quite a debugger, but it's better than just like staring at like static dumps. So the big question is, so we watch all this and like, is there actually code, right? We said like if there's code, you can watch it kind of execute, but is there actually code? We haven't found any yet. It's just kind of graphics so far and dirty words. No code. So there's no code on the external chip at all. It's just graphics and audio. So what do we even do now? So if we can't get to the code, but all we have is the graphics and the audio, we can dump all the sprites, but that's not very interesting. So can we dump the code anyway? So there's a couple of options for this, right? You either find some kind of vulnerability that gets you an information leak that can leak bytes out. You go figure out what the data sheet is and see if there's a way to dump the internal contents of that blob, the black blob microcontroller, because that's where you assume the code's at. Does the data sheet just tell you how to do it, maybe? Or you find a full-blown memory corruption vulnerability and write shellcode to dump out the bytes for you. These are all kind of your options, and every single one of them requires you to identify at least what the architecture is, because you can't write shellcode for a chip you don't even know what it is. So in order to do that, we need to figure out what the chip is. So what's underneath that blob? Problem is that the black blob is made of epoxy, and epoxy is really tough. You like fuming nitric acid, I think, is how people get through this stuff normally. I'm not doing that in my apartment. I do something much worse you'll see soon. But what we can do instead is we can just blast it with a high air gun. So all that stuff, like you drip like acid and like you send it off to get decapped, and it's this very fancy laser ablatement, all this crazy. No, you just like blast it with a hot air gun and just it crumbles, and you get this cool chip out, and it's got kind of like rainbow patterns on it. It's very cool. Supposedly you can read like the gates out of it to get the ROM out. So, but before we go try and do that, we've now pulled the chip off. So what did that do to the board? The board's not doing so hot. It has some battle damage here, but the die is off of it. It's relatively intact, and now you can see where all the little traces go, which comes in handy later for building a schematic. So let's turn our attention to the die real quick. So that's what it looks like. You can zoom in as far as you want on these big chunks here, and you won't see anything useful, unfortunately. It's covered in copper traces, so it makes it hard to see what's underneath. So you can use ferric chloride, the same stuff you use to etch PCBs, to try and etch through that copper layer to see if there's anything interesting underneath. What we're actually looking for is a logo, a marking, like a model number, just something, like what brand is this chip even, is kind of what we're going for. Maybe you match it to a die photo online, maybe. So yeah, we etch down the copper and we get this kind of cool picture that looks very neat, but doesn't actually tell us anything about the structure of the chip. There's no markings, there's no logos, there's no model number, there's no nothing. So now that you've etched down the copper, what's left? Well, what if they put their logo and stuff under a different layer? So there's, on chips, they use for insulation between the layers, they use silicon oxide, which is glass. And ferric chloride does not etch glass. What does is hydrofluoric acid. So you take a step back and consider the safety implications of whether or not you should attack your Mr. Pencil chip with hydrofluoric acid without a lab. And I had two sources for this. One was Dr. Neil Long. He has a bunch of letters after his name. And he's describing with that picture on the left the toxicology symptoms of hydrofluoric acid exposure. And as you can see, the symptoms are that you're dead and your hand is on fire. So that's kind of risk consideration A. Risk consideration B is this YouTube video by a random guy with no credentials, and he says it's okay. So you buy Wink Rust Stain Remover. Do not do this. LayerOne cannot be held responsible for any damage, etc. This is roughly 2% hydrofluoric acid, it turns out. I still wore so much protective equipment when I use this stuff. I don't care they sell it on the grocery store. This is terrifying. It leaches the calcium out of your bones or something and kills you. So after you etch the hydrofluoric, it doesn't turn it blue. That's just a side effect of the lighting. That would be neat though. Cool, so it looks different. You see different structures than you could see before, but you still don't get anything out of this. It just looks cool. And more importantly, no logos, no branding, no nothing. So what do you do next? Well, you guess what vendor or what manufacturer built this thing based on like kind of which ones work in what markets and whatnot. And you guess that it's General Plus because they make these kind of LCD microcontrollers for toys. They're like the big player from what I can tell. So you go through every single General Plus data sheet that's publicly available. You pull down their entire development environment and you go through all their header files and you still can't find it. So this is still not enough identified chip. So then you're like, okay, I don't know what the chip is. I've dumped all the sprites out. I've got the dirty word list. What do I even do next? I don't know how to do anything with this. Yeah, so you don't do anything for 2 years. But then one day, you're in Ghidra just playing around as you do, and you try 65CO2 as the architecture. And you just kind of look through this random data, bink, and you hit D for disassemble, and there's actual assembly there. See, I told you there'd be assembly in this talk. This did not happen the countless times that myself and the merry gang of Mr. Pencil hackers tried this at LayerOne, because so much of the flash chip is just like sprite data, and you're trying so many different architectures. We didn't get this run of like disassembly. It just turned into gibberish usually. But I happened to land on an area of code and hit this. And then there's another good surprise is that it's writable. So this area is also writable. It's not like locked out or nothing. So we have executable code in an architecture that we understand, and it's writable. So that sounds like a pretty good starting point for arbitrary code execution, which you remember right was one of our stretch goals. So what is 65CO2? Well, it's kind of like 65O2, which is probably like the most important instruction set or such architecture for video games. Atari 2600, some variants of Commodore 64, the Nintendo Entertainment System, the NES was all kind of based on 6502. Apple II was. So this thing is everywhere. What's not everywhere is 65CO2. It has, as far as I can tell, 3 commercially successful products. The TurboGrafx 16 from 1987, the Atari Lynx from 1989, and the Mr. Pencil from 2026. This is basically a 6502 with some extra like nice to have instructions added to it. So in theory, it'll be easier to program for if we can get code running on it. Supposedly, General Plus makes some chips with this too. So you're kind of getting closer to the assumption that was made earlier about markets and whatnot. So they don't acknowledge it though. If you go through all this stuff, they never say 6502 anywhere in anything. So can it play Doom? This is our new goal. We're no longer trying to like make it like speak swear words or reverse engineer it or learn. We're just trying to make it play Doom. So in order to play Doom, you need to get some pieces. You need to like assemble sort of your set of tools. Unfortunately, we don't know anything. We know that there's code in it. We know what instruction set it is, but we don't know how to do any of this yet. So here's the approach. We're going to try to get code execution. And the way we do this, there's a button that has a reading icon on it. If you press it, it displays a reading animation. we know from dumping the flash and going through all the sprites that the reading animation starts at the address A830. You can ignore the little 93 up here for now. Just A830. That's where the animation starts for the reading when you press the button. So if we search the entire flash for this A830, maybe we can find a pointer or like a call or something, or not a call, but a data load. So if you do that, you'll find this guy. So at the address C1A8, we see a reference to 30A8, which is just A830 backwards. So these are so now we know it's a little endian, right? And then if you look at the data after this pointer to the first frame animation, you'll see like 8F, 9. That is the address of the second frame. 99BF, that's the address of the third frame. So this is a list of pointers that are pointing at the different frames of animation. And some code is obviously reading and playing these back, right? So the next thing you do is you go hunt for this, C1A8. So that's the address of the pointer that points to the first frame of animation. So that doesn't exist anywhere. Nowhere in the entire flash will you find those like 2 bytes next to each other in a way that makes sense. But what we do find is what's on the left. Down here, they're doing the LDA means load a number into the A register. Store STA is like store A. So store the contents register A into this memory address. Those are the only 2 instructions you need to know to understand this talk, hopefully. But yeah, they're loading in A8 and C1 into A for some reason. So you make some kind of leaps of logic, you look around a little bit, and you figure out this code is reading this listing of animation frame pointers. So what this means for us is that now we know this code gets run when I press the button that makes that reading animation play. That's the big like leap there. So if I overwrite this code with my code, so JSR is a call, so it sends execution somewhere else, right, that we control. So I'm going to send execution to DDD0. What is that? It's just a spot in Flash that I have control over and I can write to. So I put my code there, I send execution there, but we have to have a way to tell that it actually worked, right? Because you'll just send it there and run some instructions and then you'll just crash because you can't recover. You have no input output. You have no idea where anything is. So even though you have you can write code and write it to Flash and supposedly get it to run, you can't tell if anything worked. So you kind of do 2 test cases. One of them, you just do what the original code did anyway, and then you jump back to where you came from before you overwrote those instructions. And this should just do nothing. It should kind of go over here for a couple of cycles, then come back. And then you put a legal instruction in the second test case and see if it crashes. And lo and behold, it works. So we have a hook where we can get control of execution by writing to this Flash chip. This is you now. So you are executing from DDD0. You came from address BF02. And other than that, you know nothing. You have no idea where anything is. Like, you want to make the lights blink or like play Doom. You can't because you don't know where any of the I/O is. You don't know how to communicate information to the user or get input or anything. You can just kind of run code. So at this point, you're lost in the forest and you have to figure out what's where. It's like a black box, but you can execute code inside of it. So the first thing that you should do is immediately stop soldering and desoldering the Flash chip every time you'll make a change. I did about 20 iterations of that, and it's not a good idea. Instead, find some way to Flash and then move it over and test. Ideally, you do it all together. You don't have to move anything. I took this chip carrier. There are 6 of them in the hardware hacking village, so you don't have to solder things. And you move it back and forth between your programming rig, which in my case was just a Raspberry Pi, and the Mr. Pencil. And now you can program it and then go test it. So you get your cycle time down is the whole idea of this. So how are we going to get information out of this thing? I want to do hello world in Mr. Pencil, right? How do I even do that? There's no print, right? There is a screen, but there's no terminal. So, well, one thing we know that we were able to read data off the SPI bus earlier. Remember, we could watch those reads happening in real time and figure out when they happened to figure out what the graphics were. That is a channel we can use to leak data out. So the idea is that if you make your shell code do memory reads from certain addresses, those will turn into SPI bus Flash reads. Like, they're reading data from the Flash just like we want to. And you can encode the data that you want to leak in the address of the Flash, of the address you're trying to read from. And then you can sniff it. So the idea is that if you read a byte from some address that you don't know what's there, let's say that there's the number 44 there, right? If you then make a read to address EE44, you don't even care what's at that address, but you care that your spy sniffing rig can see the fact that you looked for EE44, and you've now leaked a byte by doing so. So if you use that and you dump all of memory, so you dump every single address in the 16-bit address space, this is the pattern that you get. From address 8000 to FFFF, that matches part of the flash chip you already dumped. So your flash is mapped in at address 8000 is what that means. From address 00 to hex 8000, that's all new data you've never seen before. So what might this be? What is this other half of the address space that isn't in flash? What might that be? Well, it's RAM and your I/O. So there's an interesting thing here where so whenever you dump the bytes out by leaking over SPY, and you saw it match some of your flash, it only matched about 16 kilobytes, but there's 4 megabytes of flash. So how does it get to the rest of it? The answer is something called bank switching, where the chip can control via code which part of the flash it's looking at any given time. So you can kind of switch back and forth between these different banks if you can get the code to do the right thing to do that. I'll show you how it's done in 1 second. But you have to figure out how it's done because it's not standard. You can't go look it up. It's different per chip. So yeah, the idea is that we now kind of know where we're at. We know the contents of RAM. We know what's in I/O. We have shellcode executing down in what's called bank 81. This is the second kind of chunk of the flash that we dumped. So now what we want to do is be able to write code to do more exploration and figure out how does the rest of this thing work? How does bank switching work? How do we move where the flash window is? How do I get the LED slab? How do I get stuff on the screen? How do I do audio? So what you should do is take a moment and do some more harnessing. So Ghidra can't deal with this banked flash thing where you swap out the upper half of the address space all the time. It doesn't know how to deal with it. It doesn't know how to follow references. There is a 6502 compiler and an assembler. So you put some effort into that and get that working so you don't have to write everything in bytecode. You can write some assembly and build it. I recommend that. So this helps to get you oriented. So let's see if we can figure out this whole bank switching thing. How do I change what part of the flash is mapped into memory with code? So when you go traipse around kind of reverse engineering, you see this bit up here on the upper right. So they're doing, remember JSR, it's like a call where you send execution somewhere else. They're doing a JSR to address 94D9. If you go look at address 94D9 in your area of flash that you kind of know what's there, it's just Fs. So this something is different. It expects something else to be there, like a different flash bank. So you then go look at every single chunk of flash to see if at that address there is executable code, and there's not. So what that means is that there are more banks than is what's on your flash chip. So you don't have all of that. You don't have all the code, is what this means. So what we hypothesize is happening here is that they load the number 1, so LDA 1, and then they store it in the address A38. And then they do this crazy jump that goes somewhere with non-executable code that shouldn't work. So this probably means that A38 is the bank switching register. If you put a 1 there, then it will switch it instantly to bank 1 of flash. The problem is that we don't have a bank 1. We've already exhausted all the 4 megs. There's no more left. So where is this? Well, we can find out. The answer is that in your shellcode that you write into flash, so with that little flash chip that you can write to, you write some code that injects more code into RAM. So you have to copy yourself up into RAM. You're in bank 81 right now. That's where the flash is that you have control over and you can write to. That's called bank 81 in hex. That's where your shellcode lives. So you inject up into this RAM area, and then you jump to it. So now you're executing from RAM. Once you're in RAM, you write a 1 to that register A38, and that swaps out the upper half of the address space. See, it says bank 1 now instead of bank 81. Then you go read the bytes at that address that we saw we were going to get a jump to earlier, that we had all the Fs. You read a byte, you store it for a second, then you switch back to bank 81, and then you use your trick of leaking data out the SPI bus to get that single byte out. And then you automate the whole thing. And what this allows you to do is dump this bank 1 that is not in your external flash chip. This bank 1 lives inside that epoxy blob that you have no other way to get to. So you inject dumping code into RAM, and you dump 1 byte at a time, and then you leak it out of the SPI bus, is how you get access to this kind of these hidden banks of program code. So if you do that, what do you get out? What's in this hidden like bank 1 at that address it was going to jump to specifically? 94D9 was the address that we were going to call earlier. And lo and behold, in bank 1, there's code there. There's not code in any other bank. It's got to be in bank 1, and you have to get it by doing this sneaky like hidden flash dump thing. Okay, so now you use that to dump all the rest of the banks. So you get all of it. Now you have all their hidden code that all lives in that epoxy blob that they specifically don't want you to be able to read out. So what do you do now? Like, remember, we're trying to write Doom, right? So I want to get I/O working. I want to get something other than just like reading memory functional. So I want this little LED bar. It's got 3 LEDs at the top, and they flash. I want to get this thing blinking and figure out how to control that. Maybe use it as a way to get data out faster without having to sniff the SPI bus. So you write a 1 to every single address in the entire address space. It will crash. That's what it will do. So you limit it. You write to less addresses until it doesn't crash, and you kind of play with where you're writing 1s and 0s, but you're still covering a large area. Is the strategy here, and you're looking for the LEDs to light up. That's what you're going for. So you write a bunch of 1s or 0s. You try both because you don't know what the polarity is, and you get a crash. Then you're like, wait a minute. You do nothing and just loop your shell code, and you also crash. But we tested the hook earlier. It worked. So we have execution, and we know what instruction set it is. Why are we crashing? We just loop. It turns out that this thing is a high assurance, ready to go to space like NASA, Mr. Pencil. They have something called a watchdog. So if you write a 1 to the address A36 often enough, say every few milliseconds, it will not kill itself. If you don't do that, it will commit seppuku and reset itself. So this is for if you have like unexplainable hardware faults and like you want your space shuttle to still space shuttle, like you have this watchdog in hardware that like monitors to see if you got stuck. So if you're Mr. Pencil, you want to be reliable, so they do this. Cool. So every so often, we're just going to write a 1 to that address, and that keeps it alive. Once again, there's no data sheet for any of this. Like, this doesn't exist. If you go Google Mr. Pencil, like, reverse it, there's 0. There's nothing. So you have to figure all out kind of from on the inside in a black boxy sort of way. But now we can stay alive long enough that we can actually do some testing. So we know the watchdog is at A36. The bank register that swaps out kind of what flash is mapped in, that's at A38. So we kind of suspect, okay, the special registers that do stuff, maybe they're all in like A something something, so you can make your search smaller. So you write a bunch of 0s to this wide range of A something something, and you get a crash, and then you kind of slowly narrow the range until you get the LED to slide up, and eventually you can kind of converge on a single address, where if you write all 0s there, all the LEDs light up. So you do a little bit more, and you figure out exactly which bits of A01 it turns out, so it's right at the beginning. You should just try that one, it would have been easier. So if you want the left one light up, you turn that bit off, the bit number 3, and kind of on it goes. So now you have control over the LEDs. So now you can blink, you can like Morse code blink out things instead of sniffing a SPI bus if you wanted to. So you can do the same trick to find the screen, so where all the graphics are at. You write these 0s and Fs, kind of all the address space until you see something show up, is the idea. You make some assumptions about kind of what the graphics format is, because we know what the sprites are laid out as, so you can kind of assume a little bit about how the screen works. But if you don't know, just write zeros and Fs everywhere and see what happens. And if you do that, eventually you'll see this little strip of black pixels on the bottom. There's 8 of them. We wrote a byte of zeros in different places and found this. So this is how you get to the screen. You write bits to these addresses, this hex 600, 800, 700, 900, and they all show up on the screen in one way or another one, but the relationship is super weird. So if you write to the 600s, it makes a dark pixel. If you write to the 800s, it makes a light pixel. And it does the same thing for the 70s and the 90s. So there's just 4 different display buffers. And if you don't know how to turn, like I saw, a row of 8 pixels into like drawing circles and stuff, you fiddle with it until you figure the format out. It's not that bad. What's weird about this is that during each time you execute and write something to this video memory, you only see half of this. You don't ever see all of this together on one screen. I showed it to you this way to kind of visualize it. So they're obviously flipping back and forth between these 2 display buffers, like flickering to get extra shades of gray. So you want to go figure out where that's happening so you can have control over which pixels are being displayed, because it's random otherwise. So you start writing 1s and 0s all the address space again, and you watch and see which of the boxes show up on the screen when you do that. And eventually, if you tickle A80 and you write bits in these spots, you can control which of those display buffers show up. And you can even show both at the same time. There's no reason you would ever do this, I don't think, but they let you do it. So now you can write arbitrary pixels to the screen, and you get like 3 shades of gray out of it. And that combined kind of with your sprite knowledge from earlier of tearing apart the sprite format, you can kind of display graphics now as long as you can fit the code and it runs fast enough and sort of those sort of limitations. Okay, so what else can we find besides the screen, the LEDs? What other kind of output is there? On the back of the board, there's these little test pads that aren't connected to anything. They're just connected to the CPU. They don't do anything else. So in order to find these, you can hook up a logic analyzer and then start, again, you just write 1s and 0s all the address space until something lights up, right? If something crashes, then you just don't write there. And you repeat this methodology of just narrowing down kind of binary search style. And eventually you'll find neat stuff like this, where if you write to A03 to bit 4, it kills the power to the board. So that's kind of neat. And then the other test pads, it turns out, live on the other bits of this address. One of them I found by accident. So I screwed up the wiring while I was doing all this, and I accidentally tied bit 5, or this pin on the board. I accidentally tied it to ground, and the act of doing that and starting up Mr. Pencil made it go into test mode where it says freak 1 kilohertz, and it sprays out a 1 kilohertz square wave on one of the other test pads. So I don't know whether secrets are living in this firmware of like weird diagnostic modes, but I thought that was kind of fun. But if you mess with this enough, you can control if these are all inputs and outputs, and then you can write something more useful, which is a serial protocol. So you can make this thing talk serial to like a Raspberry Pi, and now you no longer have to sniff a spy bus to get access to data to do hello world. You can say hello world over a serial port that you invented from these test pads. This is me trying to read every single bank to see if there's any data at all, if we missed anything. And I used this kind of serial port that we just invented to do that. So if we go look at what the results of that scan are, the stuff that's in bright white, the 0001, 8081, those are the banks that I have looked at in depth and kind of understand what's there, roughly. The ones in gray are kind of the dumps we had before from just kind of doing the normal sort of flash dumping. With the writing it over serial, all the ones in purple are stuff I've never looked at. This is all internal inside the epoxy blob. There could be anything in there. So please go explore that. If you want firmware dumps, I will happily give them to all of you. If I had a GitHub ready for this, I should have done that. Maybe after the talk, we'll see. But there's lots of unexplored territory. There's definitely code in here. There's music. There's like a full-blown song in here for some reason that they don't use. But yeah, there's lots of unexplored territory to go play with. So now that we know kind of the layout of ROM and what's possible, what else do we have? So RAM. So this is the low addresses. This is up in that 00 to hex 8000 range. if you go and try to write a byte, like you write like the number 4 to every single part of the address space, and then you try and read it back and be like, is that a 4? And then you keep track of it. This is roughly what you end up with. The bits in green you can write to and execute code from. Everything else you can't write to. So it's either use something special or it's read-only. So what this reduces to is that if you want to do stuff in RAM, you have very, very little actual space to do it. If I'm being generous here, this is 1 kilobyte, but a bunch of that has special uses. So you really have about half a kilobyte at best to play with in RAM. So, okay, can we do Doom? That's what we're coming back to. So you hook up your logic analyzer, you have those test pads that you can kind of turn on and off, and you write a little bit of shell code, you put it in RAM, you put it in Flash, you go find their code in the internal ROM, and you measure how long does stuff take to run, so you don't know what the clock speed is yet. And it turns out if you execute code from RAM, it runs at 8 megahertz. If you run it from their internal ROM, which you don't have access to, like you can't write to that. They own that. That lives, you can read it and dump it, but like you don't get to like change that. That runs at full RAM speed, 8 megahertz. I'm very, very jealous of this. Our flash that we have write access to, the little chip that we kind of desoldered and can play with the wires, that one runs at 181 kilohertz, which is significantly slower. So Doom's going to be tough. What about input? So this surprised me. So that keypad on the front of it, that's just a big sticker. That's kind of neat. I assume there's like a board under there. No, it's just a big sticker. This is called a matrix keypad. They're documented fairly well over the internet. The way they scan it's kind of weird. I'm not going to go into it right now because we have very little time remaining. But the short version is that they scan it and they see if you bridged kind of a row and a column by pressing the button, right? So what we can do is we scan the entire address space, focusing on that A something range where we think the IO lives. We scan it, we store it, and then we hold a button down and we do it again and see like what changed. So you do that and it doesn't work. There's no consistency. Some of the bytes just change all the time randomly. There's like the other ones just stay fixed. There's no correlation between you pressing a button and that address space changing. So you scan the entire address space and you still don't find a correlation. So are you stuck? How are you going to read the keypad? No, you're not. Don't give up. Don't give up. So this is a quiz on a really wrinkly projector screen that probably doesn't help for this. So if you can read the left side, I will give you a couple of moments to see if you spot it. But the question is, given this schematic and given these I/O addresses we found earlier, remember these are the LEDs, the left, right, and center LEDs. This is the test pads on the back with the kill power bit. And where is the keypad in all of this mess? Well, right here, there are 3 LED wires coming out of the microcontroller, and then around them, there are 3 wires that go to the keypad. And then if you look where the LED byte is that controls the LED, there are 3 LED bits in a row, and they are surrounded by mystery bits. So you can kind of infer, okay, A01 must also have something to do with the keypad. But we know it's not as simple as it just like flipping on if you press a button, right? So there's something else going on. So you scan the entire address space looking for pointers, which you know are a little endian now because we saw some earlier, for 0A01. And eventually, after much pain and suffering, you will find some code that is not listed here. But this is kind of the upshot of like, what do you do once you reverse it a little bit? Basically, what you do in order to read this keypad is you piggyback off of their code, which does interact with that 0A01, where we kind of saw the correlation in the pattern of the bits and the wires. And you switch to bank 1, and you jump execution there. And then when it returns, you look in C2 and CA, and those will be filled in with some bits that correspond to what keypad button was pressed. This was a lot of fun to reverse engineer, but yeah, so now you have control of the keypad. So what do? First, to test it, you turn it into the world's worst keyboard. Remember, we have that serial kind of connection, right? Where we can send bytes over serial to a Raspberry Pi and like print them out on the screen using those test pads that we found. So you scan the keypad and then you turn it into bytes and you send it over the serial and then you display it and you sit here. This took about half an hour to get correct without typos, by the way. This is as far as I dared go because I wanted it to be an authentic screenshot, you see. We don't cheat here. But it does work. And now you have full kind of keypad control. You have control of the display, control of the LEDs. You have this test pad you can do serial on. You also go find the touchpad in a very similar way, and you figure out how that works. I clip that for time. And then at the end of all this, you can do something interesting. Yeah, you can play Doom. Watch Doom. Oh. It's a little bit simplified. It doesn't have all the levels, but let's see what happens if he kills all the monsters. I'm so excited right now. Oh, the video cut out. You'll have to go to the Hardware Hacking Village where there is a Mr. Pencil that says CTF on it.
Yeah.
There may or may not be a flag if you kill all the monsters. The problem is that there's more than 5. So it may take you a little bit. Or you can take apart Mr. Pencil and hack it and figure out how it works, or maybe make an Arduino like hit the key. I don't know. Figure it out. Be a hacker. Okay, so we got Doom running. We're going to do Quake next. Like, it's just we fully conquered this platform. No, we have not. There's so much more that remains kind of unknown about Mr. Pencil, this kind of captured UFO. The rest of the IO space, we have no idea. Can you, how do they write to Flash? We know that you can change your name. Like, where's their code that does that? Are they literally bit banging a spy bus right now to write to the Flash? I don't know, probably. What else is in all those ROM banks? We have serial. That serial protocol that I wrote is really bad. It fails, every X bytes and is unrecoverable because I don't know how to write code. Somebody write a good one for this so we can have bidirectional shells. That would be sweet. We'll write a debugger for it and the whole thing. They run 44 times as fast as our Flash code does. So if we can use their routines for audio and sprite drawing, that would be nice. I had to write my own sprite drawing code to do that Doom thing. I wish I could have just used theirs. That would have been faster and easier, but I couldn't figure out how their sprite drawing worked. Interrupts and timers. I turn my shellcode. The first thing it does is shut off all the interrupts so I don't get messed with while my shellcode's running. There's probably cool stuff in there. What is all that stuff doing? Come to the Hardware Hacking Village and hack onto Mr. Pencil. Come talk to me, or just go do it. Like I said, there's a CTF flag at the end of it if someone of you wants to dive in. Is there a monetary incentive for CTF? I don't know. The respect and admiration of your peers is all the reward that you should need. Anyway, that's me. That's my contact details. We have a little bit for questions. Anybody have any questions at all? Yeah.
So the watchdog should not be out 30 seconds or so that you find the fights.
Right. You talk about the watchdog. Yeah.
Yeah, I saw out device that is casted. Sure.
It was crashing. Yeah. So
It's more about topics.
That's an excellent question. And I'm scrolling back to wherever the thing was. There we go. Yeah, this guy. So he's talking about this watchdog timer. How do you know that you need to write a 1 to that address? There's a giant 60-bit address space. How'd you even guess? So guessing there's a watchdog timer, that's a mechanism that's in some of these microcontrollers that if I'm not doing anything but just looping and I'm getting killed, okay, it's either one of a few things. It's either interrupt firing, so interrupt is executing code that's then killing me for some reason, or it's something in hardware that's nuking me for a reason that I don't understand. That's kind of your two options. So I went really in depth with 65CO2 to make sure that I knew the interrupts were off. There's an instruction that just turns everything off, supposedly. So I kind of estimated there must be a watchdog here that's being hardware enforced. So if you go look through their code enough, you'll see where they're doing loops. They do loops just like we do. And in a bunch of their loops, there's this pattern where they just write a 1 to this place. And if you look at enough loops, you're why are they doing it? They never read from it. They just always write a 1 there. And you see it in you see it just in loops and loops and loops. And eventually you just kind of guess, maybe that's the watchdog, and you write it. The other way you could find this, I didn't do this, I found it by disassembling. But if you, again, write a 1 to everything in the address space in a loop, you have to not write 1s to stuff that kills you, right? The stuff that will crash you. But if you wrote a 1 to everywhere, you would in theory also hit the watchdog, right? So you could try that, and that would probably also get you safe enough. And then you just loop doing that. And that would be another way to discover it if you couldn't find the disassembly that clued you in. Does that help? So I gave you...
Is it kind of the wall note?
Yeah. So Ghidра's really bad at disassembling this. It has no way to know where execution goes once it jumps out of a bank. Because once you switch banks, it all goes away, right? So Ghidra doesn't even know what bank switching is. So it disassembles for about 10 instructions at a time, and then it ends. So you have to go guess where this does, and so you have to go D everywhere, or follow it manually. But yeah, if you find big enough routines, you'll see these loops that go hit a 1 in this register for no reason. It's not doing anything. And that's what I tried, and it worked. So yeah, funny enough, that register, the watchdog being at a A36, once I knew that, I Googled A36 watchdog, and there's one other person that worked on a different Leapfrog toy, and his watchdog timer was at A36. Once I saw that, I'm like, oh my God. I got it working before I looked it up, but like, it was such a confirmation, like, oh, I'm not crazy, that this makes sense. But the rest of what he found, the entire rest of the address space, all the I/O, totally different. So like I said, I still think this is a General Plus chip, but we don't know what it is, or it's custom. Yeah, still have no idea what the chip is. No data sheet, no nothing. I thought it'd be fun to make a data sheet, but all of these question marks. I think that would be a good final product. Anything else before I relinquish the stage? Okay, one more.
Please, Kevin.
Yeah.
I'll give you that. So much data.
You just read a byte into RAM. You can do it through the time, you got a little bit of space, and then you switch back so that when you read from upper addresses, it's back to flash again. And then you just make a read that has that data byte in the address. And then, but you script it all, right? You make it all automated. And then you dump it with a logic analyzer and convert it, and off you go. Doing it manually one at a time would be very long and laborious. All right. Thank you so much. I'll be outside. Please come talk to me about this. I love it.
I'll see you.